Before the break, there is a change in the program. Unfortunately, somebody has erased that change. But yeah, maybe I will write again. So the talk by Mason will be at the end of the session, and now we will. And there are some other talks, and there are some times here. So you just have to make this transformation. So now the speaker is Mehdi Assanioussi. Mehdi is my former student, and in loop quantum gravity he is already well known, so I don't have to introduce him too much. And the title of the talk, Graph Coherent States in Loop Quantum Gravity.
Thank you. Well, first I would like to thank the organizers for inviting me to give a talk on this very nice occasion, the birthday of Jurek. So yeah, as Jurek mentioned, he was my PhD supervisor, and I spent 4 years here in Warsaw. And of course, as you can imagine, there are a lot of stories happening during 4 years. But for me, there was one specific one, which is actually one of the first ones. I wasn't there alone, and it was here in the group, we had those group meetings, those bi-weekly group meetings, and it was one of the first here, so I was the new PhD students. And there were already a couple of people in the group. It was rather a big group. And we were sitting in the room, and there were like 10 people, and Jurek stood so in front of us and told us, I will tell you what are my ideas and projects for the upcoming couple of years. And then, if you feel interested in something, just tell me, and we can work on it together. And then he took the chalk and started writing on the blackboard. And there was something like that. The list looked like that. I couldn't remember the rest. It was all longer. But it started like this. First point, dynamics in LQG. Then coherent states and semi-classical limit. Matter fields coupling in LQG. Then cosmology, then black holes. And then he was really enthusiastic, explaining every subject. But the first thought that crossed my mind is, if this is a grant and this is what needs to be done, then what will be left to be done? And then he was very enthusiastic in talking about this, and at some point, everybody else was quiet. And I had this thought like that there is an emergent feeling, basically, that Jurek was imagining us in this picture. We were like the commando, and he was leading us into the realm of LQG. And he was like sitting us and motivating us. And this is basically our job and our duty. But the other impression that I had, which was for the audience, was basically that keep calm and abandon the ship while you can. But that's not true, because actually, if there is one thing about Jurek that's always true, is that he actually knows how to motivate people. And you can see that he was believing in those things. He was believing that this can be done, and it's worth to be done. And the best thing is that he manages to transfer this to the people he's talking to. So at the end of the day, and of course after a couple of years, we actually ended up being that commando. Maybe not that great, but we managed to make some achievements on the way. And I hope Jurek was happy about that at the end of the day. But of course, it's always that we are not done. So, yeah. So that brings me actually to part of that list that I showed earlier, and which is the content of my talk, which is about those graph coherent states. So this is the plan of my talk. It will start with a little motivation, a very short one. Then I will dive a bit in the concept of this graph coherent states, the construction, and I will give some examples of this construction. And I will make some comments in the end about the extensions and so on and so forth. OK, so for the motivation. So the idea of those new coherent states is based on the concept of what I call the graph change. So the graph change is simple in the sense that we have the Hilbert space of loop quantum gravity, which is chess states, and those states are labeled partly by what we call a graph. Those are finite closed graphs. And well, one can think of it simply as another quantum number. However, when you look at the algebra of operators, then you have operators, of course, that maps you from states which have different or based on different graphs, and that's okay. However, if you give it more thought, is that the issue is that if you think about operators and you think about specific operators that, for instance, are observables in your theory, or you expect them to be, in particular, for instance, if you have a Hamiltonian or any dynamics that actually changes the graph, then the question actually of having certain control and understanding the impact of this graph change, basically, which is the change in specific quantum number, it becomes really important. So that leads you naturally, if you have an operator which actually maps you between states on different graphs, then basically if you think about eigenvectors, spectrum, and so on, or any analysis of such operators, then you end up with some graph superpositions states. And actually, it was well known for a long time ago that actually one of the proposals for the dynamics is actually graph changing, which means that the graph superposition will appear in possible physical solutions. And then the other questions arise then, what would be the relevance of the graph superposition in a semi-classical limit or a continuum limit in the theory? So all those questions arise as soon as you choose to deal with those graph changing operators. Of course, you can settle to something which you say, OK, I want my dynamics to be graph preserving, and therefore most of your observables need to be also graph preserving, and therefore you reduce your problem to a restriction of, or your analysis to a restriction on the Hilbert space associated to one graph. And that actually, and you can do a lot of things there, especially that there is a lot of similarity to other fields such as lattice field theory and so on and so forth. So there is a certain machinery and certain intuition which is built in already and one can use. However, once you introduce this graph superposition, then it becomes more difficult. So the idea here first is to, if I have a set of observables which actually are graph changing and I want to study them, then I will start thinking about constructing good states that can capture certain properties of those operators. And when one thinks about good states, one gets led to the idea of coherent states. The idea of coherent states is very old, of course, and it's present in LQG for a long time. And there are many examples. So those are basically, if you look at the labeling of the states in loop quantum gravity, we have this nice basis that we call the spin networks. And there are basically, the states have three labels. You have the graph, the intertwiners, and the spins on the edges. The intertwiners sits at the vertices, and the spins on the edges. And that is basically are those three labels that label your states. And then we had, over time, there were many coherent states, kind of coherent states appearing. For instance, for the spins on the edges, there was the method of the complexifier, which was applied with the generator that was the area operator. It was very important because one has access to the spectrum of this operator, which makes the construction explicit. However, the construction of the complexifier is more general, of course. But so far, I'm not aware of other constructions using other generators, simply because there is this necessity of having a control on the generator that you choose. Also, there was, along the way, what we call coherent states for intertwiners. Those there are many. And for example, here I give the most popular example. It is called the Levin speciali coherent state intertwiners. And that uses just basically the usual coherent states in quantum mechanics for the spins, and then with a certain complex and certain average. And this is something that Simone Speciali also mentioned yesterday in the context of spin-foam amplitudes. And then the question remained open, or at least didn't gather too much attention because it was also conceptually difficult to think about extending this or trying to think about these graphs. So basically the point here, or the idea, was to see whether actually one can have certain control on those graphs somehow and construct some states that may have or reflect some nice properties with respect to some set of operators and observables. All right. So let me start with the construction concept. It's just like the ideas a bit, how to go through this construction. So the first point is that you need to define a graph change in the sense that your graph change is arbitrary. Okay? You can just take two graphs which are different, and then you can consider that the difference is basically your graph change. However, of course, it's not so trivial in the sense that you cannot consider any, or at least if you consider a certain graph change, it comes with certain complications that you need to take into account. But here I will give you just one of the simplest examples I know, and the one that I can have a very good control on, which is the one where, for instance, you have a graph, and you look at each vertex of the graphs, and then you associate or you attach a closed loop. Here, just for the technical side, it is very convenient if you are working or thinking about graph changes to work in the Hilbert space of different invariant states, because it simplifies, well, there are certain, let's say that this Hilbert space is just more adapted to this concept for now. And the point here is just to say that you have a graph change, for instance, here where I attach a closed loop to the vertex. I didn't say how yet, but just think of it as an example of that. And then you start by, your graph change is basically the action of creating, think of it as some sort of excitation at the vertices, and then you are creating excitations, exciting the vertices of your graph, and then therefore mapping it to other graphs. The second point is that, or at least the center point in this construction, is simple, is that to somehow, by this graph change, try to recover a structure of a harmonic oscillator space. And then basically the idea is that if I take again this example of the closed loops, I keep attaching more and more closed loops. And as I said, you can think of it as an excitation. And then you can count the number of excitations. Okay? So you count the number of excitations. And this is what I would call, say, if you want, would be somehow associated to or represent some sort of number operator eigenvectors. So basically, imagine an operator that you have an operator that counts basically the number of excitations, which is the number of those closed loops. And this would be an eigenvector. Here, to be specific, I'm attaching those closed loops, associating them to a pair of edges at each vertex. But that is not necessary because it again depends on the structure of the state you have, or also of the canonical structure that you want to construct. Basically, the idea is that once you have this mapping and you have this structure of the Hilbert space, you just construct the canonical coherent states that you get from the annihilation operator, basically, that you need to also introduce. But this is more or less roughly the idea. Now, this whole idea is based on a very simple key observation, is that, in general, a generic graph change with a finite structure, and by finite structure, I mean that it's really finite in the sense of you can count it if you have a set. So it's like you do not, you have a certain control that you can actually define what is an excitation. So a graph change provides a decomposition. Here I wrote that it's as I said, the Hilbert space of diff invariant states, but it doesn't have to be. For instance, one can take also the vertex Hilbert space, or one can go even to the larger Hilbert space where you have just where you average over homomorphism instead of diffeomorphism, but it's just technicalities that you can take take into account. But for now, just think of it as being on the Hilbert space of different invariant states. So this a graph change usually provides the decomposition of this space into separable subspaces that I denote H gamma A, and I'll come back to that, which are stable under the action of the operators inducing such a graph change. Okay? So this is just a simple key observation. This gamma A is what I call the ancestor graph, and it's basically a colored graph with no graph excitation. So what if whatever your excitation is that you define, there is some sort of a ground state. You have a graph where you can distinguish, once you can distinguish those excitations, you have a graph which actually you can say that has no such excitations. And that's what you identify as being the ancestor graph. And here, what I call it here, if you think about this as a graph, and you think a bit about the example that I give you with the closed loops, the space of this graph that is associated to this graph can be actually written somehow as a tensor product over those structures, those finite structures. In the example that I give you, those would be the vertices. Okay? And now each space associated to the vertex can be seen as some sort of space of finite number of harmonic oscillators. You can just imagine that it should work this way. In this case, it will be basically, for the example that I give you here, this one, it will be the number of pair of edges. If I say, for instance, that I assign a closed loop to a pair of edges, it will be the number of pair of edges at each vertex. And that would be basically this number here, omega s. This structure here, I call it S because it's not necessarily a vertex, because it depends also on what you define as your graph change or excitation. And that, depending on what you associate it to. It could be a vertex, it could be a collection of vertices. It depends. All right. So here is to give you just more or less the idea and how we get to the somehow how to clear a bit the way conceptually to get to those coherent states. Now let me give you a concrete example, and I will start again. I will go again with this example of the closed loops, as I told you, because it's the one that I can have a lot of control on. But also it gets also very interesting when I go to here. I start with the U1 gauge theory because it's an Abelian theory. It gets also more interesting when I go to non-Abelian theory because there is more structure that comes in because of the presence of the intertwiners. But I'll get back to that in a moment. So the example of closed loops in the U1 gauge theory. So in the U1 gauge theory, your states are your basis states, the spin network. They are not really spin network. I would call them just colored networks. You have, of course, some representation label on the edges, but the vertex is rather trivial. You don't have any space structure there. You are just one-dimensional. You have just the phase freedom, basically. All right. And now I can create an excitation, these closed loops. And we know that this closed loop corresponds to a holonomy. Depending now how it is contracted, but in this case, I will take just the trace of a holonomy, which is associated to a closed loop, so this closed loop. And this omega is what labels basically this wedge. So that's what basically I write here. Okay? So imagine that there is this mapping thanks to this operator. So this basically you can defines your graph excitation. Now, of course, if you keep acting multiple times with this operator, you will get other more and more loops. And the idea is that once you get a state, normalized state, you can consider a normalized state where you have a certain number of loops n associated to this wedge. Okay? And that's what you would consider as being the eigenvector of the number operator associated to the space of this wedge, which I write here. And this would be the eigenvector of the number operator. So this, roughly speaking, is that. Now, just to show you the example. Now, effectively, what you need to do is to introduce the canonical structure. So the canonical structure in this case is rather trivial because you really just are mimicking the space basically where you have excitations, but it's just L2 spaces, a tensor product of finite L2 spaces. So in fact, it's basically the same. It's basically like if you have, imagine just that you have a harmonic oscillator. And then you can consider introduce those such operators now where you have the states. So the states are simply what you call a normalized states, which has certain L loops. And that's it. That's enough in the Abelian theory to define your state. And then you define this operator, and of course you impose the canonical commutations, so that you can get them from this construction. Now you can see that it's very similar. And of course you would follow just with the simple construction to get to the canonical coherent states. That's what you, in principle, would do. Then you would wonder then, okay, then I have the states. Now you need to pay attention that now you have those states where you have some, it's a superposition of graphs with different loops. So if you see it in one wedge space, there will be a superposition of those states, okay, with certain weights, standard ones. And then you tensor product over the wedges. And that's doable in this context because you have this trivial intertwiner structure. So basically you can think of those wedges as being really just independent L2 spaces. And that's basically it, in the sense that the construction of the state goes on like that. Now, the question that you may ask afterwards is, what is the correspondence, or how should I understand those operators here with respect to the standard operators that you have in the space of LQG? Now, here to give you an example, well, the correspondence here with respect to this graph change that I chose is that actually the closed loop holonomies, or this trace of this holonomy, is actually defining this combination of those operators. The adjoint here should be understood not the adjoint of the holonomy in the group, but rather the adjoint operator that is in the space of the in the algebra of operators on this whole Hilbert space. So in other words, this operator, as I showed you before, will create this excitation, while this one will actually annihilate the excitation. And then this operator here that I put new is again it's just a simple function. Here actually the labels are not good, it's just omega. So this is just an old notation that I had. But basically this is just, this is a well-defined operator, it's invertible. So you see this square root, but basically it's just, you can write, because it's written in terms of number operator, you can have the spectral decomposition of this operator. And basically that's how, this is the relation, or this is how you define the relation between this canonical structure that you introduced and the elementary operators that you have in the loop quantum gravity. Now, a particular point that here I want to emphasize is, in this case, the whole structure, the whole construction cared only about this excitation, and therefore the part which mattered, because it comes actually directly from the structure of LQG, is the presence of holonomies. And I didn't mention anything about fluxes, because in principle in this choice that I made, I don't need to talk about the fluxes. However, if you take a closer look, and for instance, you look at certain combination of fluxes, here in the Abelian theory, if you think about a flux associated to one edge, it's basically diagonal, and it gives you just the color of that edge. Okay. And this is basically it. However, if you consider more, how I would call them more global operators, they are still functions of the fluxes, but they capture something more. Namely here, for instance, to give you the example, I defined the sum of fluxes, but it's a sum over the edges. It's a specific here, I denote it with I tilde. I say I is to label each edge in your graph. But the I tilde here is particular. For instance, if I consider loops here that are associated to the graph such that those edges, for instance, are tangent with a fixed order of tangentiality to those two edges, okay? Then there is of course what is defined is that I can call the germ, which is basically the direction defined by the tangent vector here at the vertex. Then you have many edges that actually belong to this germ. Germ, you can think of it as a class defined by this tangentiality, and here you have multiple edges in that. So this is just to give an example, and then if you sum the fluxes associated to all the edges in this germ, okay, then you actually realize that you can write it in terms of this canonical structure that one introduces. And you get here those number operators. Here, again, the labeling is wrong, but it's just think of that as a wedge, omega, and this is the wedge with the opposite orientation. And you get this expression here for an operator which actually does not depend on the holonomies. It's just a flux. It depends only on the fluxes, but it manages actually to capture this structure of the state or superposition through this sum here. And those, well, I will come back to that maybe later if I get the time, but those sums are very much present in our construction. Yes? Question?
Confused when you talk about the germ. These are diffeomorphism invariants.
Yes.
Right? So these are abstract graphs. So
Not really.
They're not really abstract graphs.
No. So you have this structure at the vertex which is still there. So you have, it's not because I average with respect to diffeomorphisms. Okay. So if you want, the tangentiality structure at the vertex remains. It is not destroyed by the diffeomorphism. It is present.
What class of diffeomorphisms are you dividing from?
Analytic diffeomorphisms.
Fully analytic, so you don't allow any non-analytic?
It depends on the Hilbert space that I would, at the end of the day, aim for. For instance, if I want to keep the tangentiality, okay, or a notion of tangentiality, then I need at least C1. Okay, if I want to stay at the tangentiality of degree 1. Okay, but I will lose any information that was higher. So here, if I want to think about it in terms of that I don't care, I don't want to put any limitation on the tangentiality, I can take C infinity. Otherwise, if you want to lose all that, then you don't you just average with respect to continuous diffeomorphism, and that will be again different. But just here, imagine that for simplicity, that you have the analytic one. Those are just details that you need to pay attention to when you are constructing your Hilbert space. But yeah, in case you lose entirely the tangentiality, okay, and you have the abstract graph, as you say, then you cannot say really that you associate to a wedge. Now, in fact, what would be the interesting structure is to say that I associate an excitation to the whole vertex, because at the end of the day, you don't distinguish really where this loop sits, but it can sit on the vertex. And then your, in a way, your L2 space will be the vertex space. And then you attach those loops. So you can extend it this way. Yes, so the thing is that you consider those operators, and then it emerges just by itself through this sum, actually, that you have, that it can depend on the canonical structure. And of course, if you have such operators, then you would expect that there are certain coherence properties that they may satisfy. But that was just an example here. It is easy to construct it here, for instance, because it's the Abelian case. It gets more complicated when you get to the non-Abelian case. Of course, you can think about those operators again. You go back to those trace of holonomies. Here I just dropped the trace for simplicity of the notation, and you can compute expectation values and the relative variance. And also you observe that this operator that depends only on the fluxes has also this interesting behavior and dependence on this complex number in the canonical coherent state. Okay, so in the context of this Abelian theory, it rather works smoothly because it really reduces to simply a structure of the L2 spaces. And what is interesting about it is that the U1 gauge theory is related to the Maxwell theory, of course. And then if you look at Maxwell field Hamiltonian, then, of course, it has the gravity part. Here I write just, this is Yang-Mills in German, but think of it as in the Abelian case. Now, there is the gravity part, which is involved also here. Usually in the constraint, there is also the GR Hamiltonian. But the thing is that the matter field part, the Yang-Mills part, actually you can entirely express it now in terms of this canonical structure that you introduced. So in other words, you can somehow, in a way, depending on those excitations that you introduce, adapt to the choice of canonical structure as much as you can to the form of the Hamiltonian, because that somehow gets you guarantees you that you get some nice properties for your dynamics with respect to those states. Right. Right, so the action of the Hamiltonian at vertex for this case is reformulated as an action in a space of finite number of harmonic oscillators. Of course, the coupling is much more complicated than a harmonic oscillator because it's just different. Nevertheless, it retains some interesting properties. So here, let me go now to the non-Abelian case with the same excitations, graph excitations that I considered. So the Hilbert structure, the Hilbert space structure, can be again decomposed in the same way as I showed. So you take this Hilbert space associated to a vertex of an ancestral graph, okay? And then you can decompose it in terms of those excitations. So basically, you separate the states depending on the number of closed loops that they have in their graph. Okay, so this is basically a Hilbert space where it contains the states in this larger space, which have n loops at the vertex. Doesn't matter where they are for now. It only matters that they have n vertex. Okay, so it's just nice to have this structure in mind. Now, to introduce the canonical structure, so you can impose, you can say, okay, you can say, let's impose this canonical structure and see if we can get one. Basically, that's the idea. You can see that by imposing those commutation relations, you get two things. So if I set, first of all, the Hilbert space associated, basically it has 0 excitations, so I end up only with the ancestor graph. So this graph, or any state that is associated that has this graph, must form like a sort of a vacuum state. So it gets annihilated by your annihilation operators. So for every annihilation operator that you have in your canonical structure, it maps this space to 0. And now, for spaces which have a certain number of excitations, now for the annihilation operator, it will remove one excitation. The issue here, of course, it maps you to this Hilbert space that is added by n-1 excitation. Now, the tricky part in the non-Abelian theory, those spaces do not have the same dimension. Okay? The structure is different because you have this intertwining. For instance, if you think about SU2, yeah, thank you. If you think about SU2, then you have this intertwining structure, and naturally, the dimension of this space is larger than the dimension of this space. Now, let me just introduce a bit of notation. I will call elements of this Hilbert space with n excitations in this form. So this stands for the intertwiner, and I number them. Well, this is just a label through the finite, because the space of intertwiner is finite dimensional. So just consider, for instance, that you choose a basis, or just select a set which spans this space, and then you have the labeling of excitations. Here, I called it n, but it's not entirely true because it's the sum of all those is n, okay? And those can be distributed over here the wedges of this vertex. Okay. Then, actually, if you work it out a bit, you can realize that you can introduce such mapping. You just postulate this action of those annihilation and creation operators in those spaces, okay? Now, here it's a bit complicated, so I will be explaining it better more in a bit of pictures. But just to show you, so this is basically the same object as here. Think of it as here. It's just that it has an additional label that I will come back to. But basically, this operator annihilates one of the excitations, the J wedge, okay? And it gives you a number with it, which is more general. So it's not anymore just the square root of n, but it has an additional combination with this m here. Now this m is basically, so to be precise, because you have different dimensions between those two spaces, okay, then this operator must annihilate a subspace, basically a subspace of dimension that is the difference between the two. So it must just annihilate part of that Hilbert space, which means that that Hilbert space is spanned by what would be vacuum states. But those are not vacuum states that have 0 excitations. They have certain excitations, but they are, if you want, more general vacuum states, because now there is, you must imagine that there are like the graph excitations, but now you have this additional freedom that is in the intertwiner space. And basically, this is what the label M is for, because this label M comes here to tell you that this state, this intertwiner with certain number of excitations here, comes actually from a vacuum state which has certain M number of excitations. So this is how it gets, how now this additional structure of the intertwiners that comes from the non-Abelian theory comes in. So to depict that a bit in a simple way, so you have the Abelian case, which is rather obvious if you think about one wedge. So think about this a wedge, one space wedge. This is the vacuum state. And then you keep mapping, if you want, by creation operators. You can go to higher and higher levels of excitations. In the non-Abelian case, you first of all has in the Hilbert space that is associated to the ancestor graph, which got more structure. Okay, it's not one-dimensional anymore, so it can have. So that's what I call here many vacuum states. Then you map those vacuum states through your creation operators, and you keep increasing the excitations for the wedge 1, for instance, here. So you get one excitation at the wedge 1, second excitation, and you can have it here as well, but starting from a different vacuum. The additional thing here is that actually on the level of one excitations, you have already also other vacuum states that are present. So this is the vacuum state, one of the vacuum states, but here is, in the picture is one, that has already, if you want this graph, in its graph, it already has an excitation, but it is still annihilated by collective annihilation operators. So in this construction, for the non-Abelian case, there are some things that arise, which is one thing is that there is this non-uniqueness of the vacuum states, and the non-uniqueness of the mapping between the G tensors. This is for generic gauge group. Basically, this mapping here, I show you one mapping, but I could as well construct a mapping such that this vacuum state is mapped to this state. The state is mapped to this state. So I have a certain freedom in the canonical structure. It's not unique on this space. And now, OK, so this point is noted. Now, these mappings are actually interesting, but their structure can actually be interesting. This is something that Christian helped me understand better when I first started working on this. So once you have this canonical structure and you select your vacuum states, then the coherent states are given. The canonical coherent states are just given to you. Of course, they satisfy, again, all those properties. Now you can consider the identification, again, with the operators in LQG can be made. Here I gave you two examples. So for instance, this is, as you can easily say, C is not gauge invariant, but this is gauge invariant. But of course, they give you different mappings between the intertwiners in your Hilbert space. And of course, you have some coherence properties that get satisfied. OK, so just to conclude, I want to make here some comments. So the comments in the construction, that there are important points in the construction, is that you can, once you select a graph change, you need to have a graph change which can give you actually this structure of the Hilbert space, where the Hilbert space is separable, and you have this finite structure that you can actually control. Here, various valid graph changes are actually possible, including the ones that, for instance, I lost the chalk. Including the ones that, for instance, were introduced for the Hamiltonian in Tiemann's Hamiltonian. So you can introduce that, but you need to pay attention now, because it's not anymore only the intertwined structure that makes your life complicated. But if you have multiple wedges, then you have to pay attention to this, because this would be, for instance, different from the other combination here. Okay, and this matters because this basically tells you that if you take the naive canonical structure that I took here with wedges, it won't work, because your canonical operators will not commute or will not satisfy the canonical commutation rules. However, this is also solvable, similarly to what I was mentioning to you. The thing here is that you just should not think about the wedge as being your L2 space, but actually take the whole vertex. And then you have to construct your canonical structure, which is basically symmetric with respect to the excitation of the wedges. And then you can get, again, certain canonical structure here. As I mentioned, there is the freedom in the choice of vacuum states and tensor mappings, but that is also nice because that means that you have a certain freedom in adapting the choice of coherent states, so those graph coherent states, to the choice of observables you would be interested in. Here I give you a generic in the construction generic intertwiners. I've been talking about any properties of the intertwiners, but one can also consider coherent intertwiners for the mapping and map actually specifically from one coherent intertwiner to the other. And you impose that in your canonical structure. And we know that those coherent intertwiners also have some nice properties, some classical properties with respect to certain observables. The last point here for the comment is that if in all what I showed you, there was a canonical structure in the example that depends only on the holonomies, but actually one can construct the ones that depend on fluxes. Again, what happens here is that the complication comes from the fact that fluxes do not commute in the non-Abelian case. So you need to be careful again with this operator, because this, for instance, here, if you fix the edge, and you say, I want just one flux corresponding to one edge, and then you attach the loops for it, what you are talking about here is actually not the excitation or how you associate the loop in the graph, but rather your intertwiners mapping. The intertwiner mapping will be here is specific, and this will be actually satisfying your canonical commutation rules, and it will be fine. But there are also more general ones, but there are some technicalities one needs to take care of when one introduces the fluxes, namely, you can see it as some normalization procedure that need to be done. So to summarize, the work here was about this introducing those new coherent states, which is a bit graph coherence. That is, you have this, now you introduce some coherence for those operators that actually, for which the graph change matters. The construction method is rather general. It can apply to various graphs as long as you have they satisfy those properties. And of course, you have this flexibility in the mapping of the intertwiner space, which would be actually interesting to play with. As an outlook, I see that actually one can explore the dynamics of such states. If you construct the proper states with respect to the Hamiltonian that you have in mind, then you have such freedom, and it would be interesting to see how things go. Explore the possible choices for the intertwiners mapping. As I said, coherent intertwiners or specific intertwiners as, for instance, eigenvectors of certain operators that live in the intertwiner space might be interesting. And then, of course, explore different graph excitations for the purpose of investigating semiclassical continuum limits. And that's, again, it goes back to the question of the dynamics and how you would like to control those operators. All right, thank you very much, and thank you, Jurek, for many things, and happy birthday. Thank you.
So I think we used also time for questions. So unless, okay, Thomas.
I actually have two questions which are kind of related. So you were talking, I guess, in the context of a diffeomorphism invariant Hilbert space, but you are simultaneously talking about fluxes and holonomies, which are not diffeomorphism invariant. So can you explain this a little bit more?
Yes.
So before you answer, maybe I ask also the second question because it's related. So in particular, if the surface of the flux that you're talking about is very close to the vertex, and you have many excitations, you can have very, very large flux expectation values. So if you are strictly in the diffeomorphism invariant context, then one operator that you would like to test is probably the volume operator. I mean, the volume of the whole slice, and that can also have very large expectations.
Yes.
Expectation values. So what's your take on that?
So to answer your first question about those operators, so you can consider that they've been sloppy in the bit language, but that was only to picture more or less the action of the operators. But the operators are mapped by duality. So at first they are defined in the kinematical Hilbert space, and then I define the operator. Then I map them by duality to the dual space of the dense set. Then I don't refer. I can as well not refer to the fluxes and holonomies as such, but these are new operators just defined by the dual mapping of the action of certain operators in the kinematical Hilbert space.
But even that dual mapping will map you out of the diffeomorphism invariant state.
Sorry?
Even that dual mapping will map you out of the space of diffeomorphism invariant states.
Yes, I mean the dual mapping would, but then I would average and then how to say, reduce my space and also the operators, so that basically, if you want, I write it as holonomy to depict it, but just imagine that it's simply an action of or a mapping between one diff state to another, which is one simple excitation of the graph.
So you have the dual action, then you group average after
Yes,
that.
yes, and then I group average. So this is basically exactly what happens for the Hamiltonian constraints, for instance, if you want to map to the dual space. So that you have this dual mapping again. And of course, it's a bit sloppy to say fluxes and holonomies, but you can just think of it as being the action of an operator that you mapped, the dual operator, if you want. For the second question about those divergences, I personally didn't check those divergences. They only checked the sums, but for those states, so for those coherent states, there is this. It's some sort of every component comes with a weight. So it's not necessarily. At the end of the day, it depends whether this weight converges or not. So I would say my guess is that you would need to pay attention to some normalization issues, and see whether actually, for instance, if I think about the volume and I think naively that you have this factor of j to power 3/2 in the spin. So you have this j to power 3/2 that appears in front of your states. And say I take even the intertwiner mapping such that I map from an eigenvector of the volume to another, just with a different graph. Then I get those more or less factors of j to 3/2 in my state in this infinite sum. Then the question that I would say, what is the norm of this state? And the norm of this state, I can compute it, and it will be a function of those spins, but also this z. And the question is whether this equation that you would get, to make it finite, whether there is a choice of z's or not. So that would be the question.
I was thinking that your states are anyway normalized, right?
Yes, those states are normalized. Yes, those states are normalized. Yeah.
I'm sorry, but we have some delay, and the next speaker is already waiting. So let us thank